In this lab, I will demonstrate the evolution of techniques for integrating tools with AI agents. We will begin by creating an AI agent that interacts with the backend system using native tool calling. Then we will expose the same backend capabilities through an MCP server and use an MCP client to automatically discover and invoke the available tools. As MCP adoption grows, organizations can quickly accumulate hundreds of tools. Exposing all of them to the model at the time of reasoning can increase the cost and latency, and it can also reduce the accuracy of tool selection. Towards the end of the lab, I will demonstrate how skills can help address this challenge by organizing tools around repeatable business outcomes such as resolve a support ticket or create a billing report, etc. Rather than sending all available tools, agents can match users' query with skills and retrieve the tools that are relevant to the current task. As a first step in our lab, we will install some packages. We will install LangGraph that we will use for creating our AI agent, MCP and LangChain MCP adapters for creating MCP server and client, and LangChain AWS for invoking Amazon Bedrock. We will use Amazon Nova Pro as the large language model for our lab. In this cell, we are defining a call to invoke the large language model. We are using Chat Bedrock Converse, which is a wrapper around Amazon Bedrock's Converse API. Notice that the temperature is set to 0 in this call. This is to make the model's response deterministic and repeatable. It will help us compare native tool calling with MCP and skills, as we will be able to focus on the architectural differences rather than random variations in model behavior. In this cell, we are defining the backend system. This represents the business logic that already exists in most organizations. In our example, we have a support ticket system that contains some example incident tickets and their associated runbooks. We will test our AI agent by finding runbooks for a support issue. There is nothing AI specific here. We have ordinary Python methods for getting the ticket status and searching the runbooks. And this is very similar to how AI agents interact with existing APIs or functionality within the enterprise systems. AI agents do not replace existing systems, rather, they orchestrate and consume them. In this cell, we are transforming the backend functions that we just saw into tools that agents can consume. This is like the integration code that you would write for connecting with an external service. The add tool decorator from LangChain will automatically extract the metadata such as description and schema definition from the functions. We will use this information for passing to large language model at the time of reasoning. Notice I also have a print command for observing the description and schema that the add tool decorator will extract for get ticket status function. And we can see that it extracts description by reading the comments in the function, and it also creates a schema which will help the model create a tool call with the right format. In this cell, we are binding the two tools that we have created with the large language model. When we do this, something very interesting happens. The tool definitions, including their descriptions and parameter schemas, are automatically shared with the model at the time of reasoning. We will not need to pass them explicitly in our code. As a next step, we will design a very simple AI agent using LangGraph and place these tools inside the agent loop. LangGraph introduces a few simple concepts for building agent workflows. Let's get familiar with some of these concepts. Nodes represent the work that is performed by the agent, such as call a large language model or invoke a tool. Edges connect two nodes and define the flow of control, determining which node executes next. Edges can also be conditional, as they can evaluate a condition and route the execution down to different paths depending upon the outcome. For example, a conditional edge can decide whether a tool call needs to be made or the response is ready to be delivered to the end user. Another important component of agent workflow is the shared state, which acts as the workflow's memory. It stores the session information, which is read and updated by all nodes in the agent. In the agent that we will define in this lab, we will begin by calling the large language model node for reasoning over the user's problem and the available tools. Every node will read the input from shared state and it will write the response or output to the shared state. So, in this case, if the model determines that it needs additional information, it will generate a tool call that it will log in the shared state, otherwise, it will produce the final answer. The router, which is the conditional edge, will look at the latest messages in the shared state from the large language model and it will determine if the flow needs to be routed to the tools node or a final response should be returned to the end user, ending the flow. The tools node will read the shared state to learn which tool has to be executed and it will execute the tool and write the response to the shared state. And then flow will be passed to the large language model node again for observing the tool response, and this will create a react loop. The model will reason over that tool response and determine the next steps. Let us look at the code itself. Here we are first defining the state. In our example, the state consists of a list of messages which represent the ongoing conversation. The first node that we are defining is the large language model node. This node invokes the model with the current conversation history. Remember, we had bound the tools with the large language model, so the model will know what tools are available to reason over in the current state. The routing function acts as the conditional edge that we saw in the diagram. It reads model's latest response from the shared state and then determines the next node, which can be tools node or end of processing. And for the tools node, we are using the pre-built tools node from LangGraph. It executes whichever tool model has selected and appends the results back in the shared state. And finally, we are connecting everything together into the graph. We are creating a state graph by passing the state object. Then we are configuring the two nodes that we had defined, the large language model node and the tool node. The workflow starts at the large language model node, so we are creating an edge between start and LLM node. Then we are configuring the conditional edge using the route after LLM function that we had created. And finally, we are creating an edge between the tools node and the large language model node for observing the tool's output. Let us test our agent by passing the user's request, which is check the ticket INC 100 and tell me which runbook system is most relevant. We are invoking the agent by passing the user's message in the human message object by LangChain. Human message or system message are LangChain objects for structured representations of the conversation. This is needed because agent framework needs to track who said what. Notice that we are writing the user message in the shared state before invoking and reading the response from the shared state as well. We are then printing the messages to observe the execution flow. So in the execution flow, we see that the human message was sent to the large language model and it reasoned to determine the most relevant runbook for ticket INC 100. I first need to get details of the ticket using get ticket status tool. Once I have the ticket details, I can use search runbooks tool to find the most relevant runbook system. So we can see that the model requested the get ticket status tool call and the system invoked the tool call. and found the status information, which is investigating login failures in identity service. This response was passed back to the large language model, and it reasoned that the ticket details indicate the issue is related to login failures in identity service. I will use the search runbooks tool to find the most relevant runbook system for this issue. And then it creates a tool call for search runbooks with the parameter login failures in identity service. And the system invoked the tool and retrieved two runbooks, identity runbook system and platform observability runbook system. This output was again passed to the large language model, and it reasoned that the searchbook runbooks tool has returned two runbook systems. And it says the identity runbook system is more specific to the identity issue and login failures, making it most relevant runbook system for ticket INC 100. So we saw that with native tool calling, we defined the tool integration with backend system locally inside the application. If you remember, we had added the tool decorator from LangChain in the integration code. Now, as a next step, we will introduce the same capability using MCP, where we will move the tool integration with the backend service in the MCP server and expose the tools. We will use the MCP client, which is embedded in the agent, to dynamically discover these tools at runtime and invoke them. To implement the MCP server, we need the fast MCP class from the MCP package that we had installed. The backend logic remains the same. This is a demo, so I have copied the entire backend system code here. In real world, your backend system will probably be somewhere on the network as a service or API, and you would write integration code in the MCP server. The MCP server definition starts here. We create an instance of fast MCP, and then we decorate the two functions using add MCP tool decorator. This publishes the capabilities in the standardized format so that any MCP compatible client can discover and consume these capabilities. And the core idea here is that MCP decouples the capability providers from capability consumers. The benefit of doing this is that the backend system can publish services independently, and the agent teams can reuse them without custom integrations. In this cell, we are defining the MCP client that will help us interact with the MCP server. And as you can see, we are running the MCP server locally as a subprocess and communicating with it using stdio. MCP servers can also be hosted as a standalone server, and MCP client in that case can communicate with it using HTTP with server sent events or WebSockets. And in this cell, we are connecting with MCP server and dynamically retrieving the tools that it exposes. This is different than native tool calling, where we define the tools locally. MCP client is basically asking the MCP server, what capabilities do you expose? And server returns the two capabilities that we had defined, which is get ticket status and search runbooks. Now let us review the AI agent code, which is same as our previous code, except that instead of binding with the local tools, now we are binding with MCP tools. We are passing them in the tools node as well. And here we are running the same test as we did with native tool calling. And we see we have a very similar response. The agent requested get ticket status tool call and then search runbooks tool call, and it returned the identity runbook system as the runbook. With MCP, we saw that we were able to decouple the agent and backend services. MCP server maintained the integration code with the backend services and exposed the capabilities as MCP tools. We were very easily able to query the tools dynamically at runtime and consume them in our agentic flow. And this creates a very dynamic flow as MCP servers can expose additional tools or change tool schemas behind the scenes without affecting the agent functionality. This can be beneficial in some cases, but for many enterprise teams, this can also create some challenges. First, the MCP servers can expose multiple tools that agent does not need for its use case. Unnecessary tools can increase the input token length for large language model. Another challenge with MCP's dynamic tool discovery is that it can provide access to unapproved tools which can cause security or policy threat for many teams. Therefore, in enterprise settings, a common solution is to retrieve only approved and relevant tools for the user's request. One way to do that is to define skills that allow us to organize tools based on business capabilities. A skill contains metadata such as name, description, the business outcome, instructions for the large language model, some examples of the matching user's query, and most importantly, the tools that are associated with the skill. At runtime, the agent matches user's intent with the skill and restricts the tool usage to the tools that are defined within the skill. There are multiple ways to define the skill registry. You can create a YAML file of skill metadata. You can save them in database. And you can also index skills in a vector database for vector semantic search. In this demo, I have hard coded the tools within the skill, but an alternate approach can be to define a policy to dynamically match available tools to the skill to make tool association more dynamic. The key idea here is that we want to extract only the relevant tools from amongst the available tools for sending to the large language model. For our use case, we are defining the skill for resolve incident and we have associated it with both our tools. We are doing so because we have limited tools and this is a demo. In real world, the idea here is to have a subset of tools associated with the skills. Next, we are defining the LangGraph shared state and we are extending the state with two additional fields, active skill and selected tool names. In this implementation of Agent Graph, we need an additional node for classifying the skill. So we are defining the node here by extracting the user input from shared state and checking for specific keywords to match the input with resolved incident skill. Notice we are saving the active skill and selected tool names in the shared state. We need the subset of tools that are exposed by both the skill and MCP server, and that is what we are doing here. And this is where the skill begins to influence the agent's behavior. In this node, which is the LLM node, we are extracting the active skill and selected tools from the shared state. We are then binding the tools dynamically with the large language model for reasoning. This is the tool node which executes the tools that are selected by the active skill and chosen by the model. Notice if no tools were selected, we are doing nothing here. Otherwise, we are invoking the approved tools. This provides another layer of control as agent acts with the boundaries that are defined by the selected skill. The route after LLM code is the same as before. The agent configuration is the same as before except for the new node that we have added for classifying the skill before the call to large language model is made. And we are starting our flow by classifying the skill. Let's test our agent by using the same query. And you can see we have a very similar response. The key takeaway here is that MCP standardizes the capabilities and skills organize these capabilities around business outcomes, helping agents reason more effectively as the ecosystem scales. And this concludes our lab for today, where we contrasted native tool calling with MCP and we added skills on top of that.